question to check last time. I've already done like pretty much all the simulation stuff that I needed to. But like I don't need this, right?
No, you don't.
Yeah, because I like saw that pop up and I know that you said that this is supposed to be like culmination of stuff you did for other things. And I saw that pop up and I'm like, I don't remember that.
Oh yeah. No, it's yeah. Although interestingly, we'll see. I think it's next week. I think next week we're doing optimization, and so we'll actually see what that's used for next week. Although I still need to make the activity for that one. So, but yeah, so we'll understand. But for this one, don't worry about it. Yeah.
Okay.
All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Great.
Good, good. 2 days before the project is due. So I saw a couple people turn in already. So thank you thank you guys for turning in early. But remember, the project is due Friday at 11:59. Okay. And so make sure you get that in. But just from kind of talking to people in the class and kind of seeing the progress of report, seems like mostly everyone's in good shape right now. And so you guys have been doing well. So I'm looking forward to reading the reports. All right. So the plan for today is we're going to, we did like 5 minutes of it last time, but, we're going to basically start our lecture notes on nonlinearities. Okay. And so, basically what we're going to describe here are, what nonlinearities mean and how to account for these in ANSYS. Okay. This is going to be another set of lecture notes that we're going to probably postpone for a couple weeks because next week we're going to be doing another ANSYS activity, right? And so next week is going to be ANSYS activity 6, which I believe is optimization. Okay, I might be wrong. It might be modal analysis, but I'm pretty sure that it's optimization. Okay, and so just like we did for transient simulations, I have a lecture planned for Monday, which kind of describes what optimization is and what you're kind of hoping to do with it in ANSYS. And then Wednesday we're going to do an activity. And so next week we have kind of a paired lecture and activity. And so, I do want to finish these lecture notes on nonlinearities because I think they're important, but probably we're going to push that off until 2 weeks. Okay. And so hopefully we get halfway done today and then we finish the other half later. Okay. All right. And I know probably everyone's focused on the midterm project right now, but I am starting to think about the final project a little bit. Okay. And so I want to assign the final project, maybe not next week because I want to give you guys a break. But probably early the week after that, and I'll sign the final project. Okay. And just to give you guys just kind of a sense of timing, the final project, which is going to be the big deliverable that you do for this class, this is going to be due Monday, December 20th. Okay. Final project. So remember, we don't have any exams in this class. Just because, I think it would be kind of awkward with, basically we're doing so much ANSYS, okay? And so, the two main graded deliverables that you're turning in is one is the midterm project, which you're turning in on Friday, and the other is the final project, okay? I still have to do a lot of thinking of how I want the final project to form, but I at least want to give you the due date, okay? So the due date is going to be Monday, December 20th at 11:59 p.m. And so this is the Monday after finals week. And so I want to give you some flexibility because I know some of you are taking other classes as well. And so I don't want to have it due during finals week because, I think that time you should focus on your final exams. And so this is going to be due after that. Okay. But with that said, I can't push this due date back any further. So this is the absolute last time that I can have this due because I have to get all my grading done before Christmas. And so that includes this class, and that includes the 3 other classes that I'm grading as well, okay? And so I'm having all my final projects due on the same day. So, there's this date is inflexible because it's as far back as I could push it already, okay? Because otherwise, then I don't see my family for Christmas, and that's not good, okay? All right. Right, and so there will be more details on the final project. Not next week, but probably the week after that. And so we'll dedicate some class time to talking about it, what I expect from it. But what I'm thinking of is, it's going to be very similar to your midterm project, but there's going to be some added requirements on top of that. Okay, and so there's going to be things like you have to do a mesh convergence test, and I want you to factor in, some of the ANSYS features that we've been learning in the later half of the course. Okay. And so what I'm thinking right now is that, I have to decide what geometry I want to give you guys. But once I give it to you, then you would do basically everything you did for the midterm project, plus a mesh convergence test. Plus you would have to incorporate 2 out of the 4 features that we learned in ANSYS from activities 5 through 8, okay? And so that's 4 activities, and so you basically have to choose 2 of them to incorporate. Yeah.
You're gonna give us the CAD model?
Yes, I'm gonna give you the CAD model. Yeah. Yeah, once we learn optimization next week, you'll learn why I have to give you the CAD model. All right, any questions on anything before we get started? Yep. I don't, and so I want to, because this is a graduate course, I want to dive a lot into a lot of the advanced features, and so a lot of the advanced features are kind of in structural mechanics, but we will go over how to do heat transfer simulations in ANSYS. It's just there's not going to be any activities, and it's not going to be part of the final project, but we will cover it. Yeah. Okay. All right, and so let's go ahead and dive into nonlinearities. Okay. All right. And so, for the last 5 minutes of class on Monday, we introduced this idea of nonlinearities, okay? Or more like we introduced the idea of linearity, okay? And so generally when engineers or scientists or, just about anyone in science say that a situation is linear, it's a very kind of loaded term that could mean a lot of different things. But for FEA, when we say a situation is linear, what we generally mean by this is that the relationship between the loading and the response, okay, is directly proportional. Okay. Okay. All right, and so, last time we did an example of a cantilever beam. Right? And so let's say that we have a beam that looks like this, okay? And let's say that we applied a load of, let's say maybe we apply a load of 1,000 newtons, okay? And the deformation that we get, maybe we get a deformation of 3 centimeters. Okay. Okay. If we're assuming linearity, and so if we assume linear behavior, okay, and we take the same beam, exact same geometry, exact same dimensions, but we cut the load in half, right? Or we did that last time. Yeah, we'll do the same thing. Okay. All right, and so let's say we cut the load in half, then what we expect is that the structural response should also be cut in half as well, right? Okay, and so the deformation that we get, let's say that it deforms, maybe like this. Okay. Okay. Then the deformation should also be half of what it was before. Okay. Okay. Intuitively, that's kind of what we expect. And when I think of linear behavior, I think of this is how kind of a reasonable person should expect things to behave. Okay. Right. Because I think it's just very natural to kind of think in a linear way, right? And so if you drink an entire can of Coke, you know that you're giving yourself diabetes, right? But if you only drink half a can of Coke, maybe you're only giving yourself half diabetes, right? And so that's just kind of naturally how people think. And so when you're thinking about FEA, you think of the same things as well. Okay. But the reality is that a lot of these structural responses to these loads are not linear. Okay. And so sometimes under certain situations, the deformation is not going to be half, right? If you have the load. Okay. And so when this happens, this is this is what's called nonlinear behavior or nonlinearities. And so what we're going to discuss in this set of lecture notes is what causes these nonlinear behaviors, what are the main culprits, basically, okay, and what are the main ways that you can actually account for this in ANSYS, okay. All right. Any questions on this? And so, nonlinearity is actually something that's really important because for every single structure out there in the world, there's always going to be some degree of nonlinear behavior. Right, and so it's always there, and so nonlinearity is not something that you can escape from. Okay, and so there's if you're doing a linear simulation, you're always going to be ignoring these effects. Okay, but luckily for us, for a lot of situations, given certain conditions are met, we can kind of ignore these nonlinear effects because they're mostly pretty negligible. Okay. Okay. And so, I tell you this because, I don't want you to think that everything we've been doing up to this point has been useless, right? Because everything we've been doing up to this point has been linear analysis. But, for a lot of the cases we've considered, they're reasonable approximations because the nonlinear effects are going to be pretty negligible. Okay. All right, and so with that said, let's talk about the three main causes of nonlinear behavior in FEA. Okay. Right, and so this is strictly with respect to structural FEA. And so for other physics types, and so for things like heat transfer, things like fluid mechanics, they have their own causes for nonlinearity as well. And so all those equations have nonlinearities associated with them. It's just the causes are different. And so, when I talk about these three things as causes for nonlinearity, this is strictly just for structural simulations. Okay. All right. So number one, this is probably the most common case for nonlinearity. And number one comes from large deformations. Okay. And so by large deformations, what I mean are deformations that cause the structure to change significantly from its original configuration. Okay. Right. And so, of course, this is a fairly relative term, and so you'll notice that I didn't put any numbers on this. Okay, mostly just because it's kind of on a very case by case basis. Okay, but generally, if you want to describe kind of this source of nonlinearities in one kind of simple statement, any deformations that cause significant distortions is gonna be the cause for nonlinear behavior. Okay? And the main source of this that we'll talk about right after this is that when you have large deformations, then the elements themselves in the in the finite element mesh become distorted. Okay. Okay. And as the elements themselves become distorted, that's going to cause some nonlinear behavior. Okay. All right, number two. And so the number two cause for nonlinearities is topology nonlinearity. And so what this refers to is situations which cause the connections or the contacts to change. Okay. Okay. Right. And so, remember for the last two activities, we've had assemblies of parts, and we've had to describe, how those parts interact with each other. Okay. So we've mostly just been using bonded connections between parts, and that's fine. But what we'll discuss later is, what do all the other options mean and how they introduce nonlinearities. Okay? Because what can happen sometimes is that when you have two parts that can slip past each other, okay? When parts slip past each other or otherwise separate, what this does is that it changes how the different nodes are connected in your mesh, right? And so when that can change, especially as a function of time, this is going to cause some nonlinearities as well. Okay? And so we'll talk about, what are all the different connection types you can have in ANSYS and what do they all mean, and which ones have the potential to introduce nonlinearities. Okay. All right. Any questions on this so far? Okay. All right. So that's the second one. Okay. And so the third one we've talked a little bit about in the past, kind of near the beginning of class, but that has to do with the material model itself. Okay. And so number 3 is material nonlinearity. Okay. And so what this refers to are, specific material models, maybe say that you have plastic deformation or you have a hyperelastic material. And so this is when the material itself has a nonlinear stress-strain relationship. Okay. All right, and so at the end of this nonlinearity lecture notes, we'll talk again about plastic deformation, what it is, how that affects the stress-strain relationship, and we'll do a little bit of a deeper discussion of hyperelasticity and what those are used for. Okay. All right, any questions on this? Okay. All right. And so in general, all of these things are good. And so, if you can include all of these into your model, you're going to have a more realistic simulation. Okay. Because remember, all structures are nonlinear to a certain degree. But just be careful that, the more nonlinearities you introduce into your FEA, the more computationally expensive it's going to be. And so it's just like anything else we've been doing in finite elements. And so, the phrase, there's no free lunch is appropriate here. Okay? And so usually if you want more accuracy, in some way or the other, you're going to have to pay for it in some way. Okay? And so nonlinear simulations, they in general take a lot longer than linear ones. But sometimes those nonlinearities are really important. All right. And so, these are the 3 causes. And so I'm going to go through each one individually and kind of give a deeper discussion of why this causes nonlinear behavior and what you can do in ANSYS to properly account for it. Okay. All right, so let's start with geometric nonlinearity, or the large deformations. Okay. right? And just like just like we mentioned on the previous page, the main reason this causes nonlinearity is because the elements and the mesh get distorted with large deformations. Okay. Right. And so we've already talked about in advanced meshing that, the quality of your mesh or the skewness of the elements, has an impact on your simulation results, right? And so if you start to have large deformations that causes your elements become, more skew, then that's obviously going to have a negative effect on your simulation results. Okay. And the main reason for that is that the computation of the stiffness of each element depends strongly on its geometry. Okay. And so for linear simulations, being when the deformations are small, right? For small deformations, before and after you apply the load, the element has roughly the same shape. Okay. And so, when the element has the same shape, before and after the loads, then this is basically not an issue. Okay. And so basically what you're saying is that the stiffness of the structure is the same, before and after you apply the loads, which is what you want, right? Because a real life structure, a real life structure is not broken up into elements, right? And so, for a real life structure, if like, so let's say that chair, right? And so that chair right now, if we kind of bent it like that, the stiffness of the chair should stay about the same because it's the same physical object, right? And so this extra kind of stiffness component from the geometry is strictly a finite element thing, right? And so we want to make sure that we limit these, as much as possible. Okay. All right. Any questions on this? Okay. All right. And so, I want to kind of maybe backtrack a little bit. And so I don't want to say that large deformations are bad, right? Sometimes when you run a simulation, large deformations are just a necessity, right? When you apply a certain load on a machine, or you apply a certain load on a structure, sometimes it's just naturally going to deform a lot, and that's something that's unavoidable. And so large deformations are not bad. What can be bad or what can be inaccurate is how you approach those large deformation states. Okay. All right, and so, to kind of illustrate this, I'm going to give you kind of two different paths, right? And so let's say that we have a quadrilateral element, okay? Right? And this quadrilateral element is going to be exposed to a very, very large amount of force, right? And so let's say that, we're applying a very large amount of force on this corner, okay? So this is going to be F big boy, okay? And so because that F is so big, it's going to cause this element to distort, okay? And so I'm going to propose basically two different ways that we can apply this force. Okay. All right. And so on the left path, let's say that we basically apply this load all at once, okay? And so on the left side, we're going to have a situation where we have this element. It's just sitting there, just minding its own business. And all of a sudden it has this, big boy force, applied on it right away. Okay. Of course, this element is going to distort. Okay. And so maybe it distorts something maybe like this. Okay. All right, and so we get a certain kind of deformation in the element. Okay. Okay. On the other side, we're going to apply this load in small steps, right? And so we're going to start with our base element, and then maybe we apply only 1/10 of the load first. Okay. And so if we apply only 1/10 of the load, maybe we get a situation that looks like this. Okay. Okay. And so on here, maybe we're only applying 1/10 of F big boy. Okay. Okay. Then in the next step, we increase that load, right? And so we, now that the element is only distorted a little bit, we increase the load by, maybe let's say we do 2/10. Okay. Okay, and so we increase the load by 2/10. Okay. Now this is maybe 2/10 of F big boy. Okay. And then we continue this until, we keep applying this in smaller steps until we reach the final deformation state. Okay. Where we have the entire load being applied. Okay. Okay, just like that. Okay. All right. And so I try to draw this in as kind of as visually as I can, but you can see that, when we, on these two paths, even though in the end we get the exact same, the exact same amount of force being applied, the two deformations look different, right? And so here we kind of have something weird going on, but on the right side, we have something a bit more stable, okay? The difference between these paths is that, when we apply the load all at once, this element deforms a lot all of a sudden. Okay. Okay. Right. And so because of that, this path on the left right here is not going to be as reliable as the one on the right. Okay. Because it's a little bit too much deformation all at once. Okay. Whereas on the right, even though in the end, we may end up with a lot of deformation, in between each of the steps, we maybe only have a small deformation. Okay. And so this is typically how you deal with situations with large deformation. Okay. And so when you have a large deformation, it helps a lot to apply the load incrementally. Okay. And so when you do that, then you are much more likely to get a deformation field that's more accurate because you only apply the load in smaller steps. And so the element has a chance to kind of deform little bit by little bit as it goes there. Okay. But when you suddenly kind of apply all the deformation at once, because the stiffness of the element depends, on its geometry, it may not properly adjust to it. Just because you go from one configuration and then all of a sudden you're in a different configuration altogether. Okay. All right, and so this is typically how you deal with situations with large deformation, is that you apply the load incrementally like this. And so the large deformation that you get is reliable and more so than before. Okay. All right. Any questions on this? Okay. All right. And so the main takeaway from this point here is that when you have large deformations, is that the structural response depends strongly on the time history of loading. Okay. And so, we don't often think of time history when we're doing static situations, right? And so when we're doing a static simulation, we have this kind of, I think, impression that, we start with the structure at rest and then we apply the load and then it instantaneously kind of deforms into what it needs to be, okay? But in reality, when we apply loads on a structure, that all the deformation usually doesn't happen right away, right? Unless there's something, else happening like buckling, right? Unless there's something like that, it usually takes at least a little bit of time in order to deform a structure, right? And so I took this pen and I tried to break it, with my hands, right? Then it would take some time for me to apply a large force. The pen would deform itself, it would start bending, and then once it kind of reaches a critical point, then it would kind of snap. But there is some time for that. Okay. And so when you're considering large deformations, you have to kind of respect that the time history. Okay. All right. And so in ANSYS, the way that you apply this is you want to make sure that your loads are being ramped up incrementally. Okay. And the nice thing about this is that there's kind of a very natural way to apply this in ANSYS. And so, you don't have to kind of manually run, say 10 simulations where you increase the load each time. There's settings within ANSYS where you can say, ramp up my load, in 10 steps or so, and ANSYS will do that automatically. Okay. And actually, I think now it's even just a checkbox. And so, I think some of you have found it already. And so, in ANSYS, there's a setting that you can set for large deformations, and all you have to do is really just turn that on. And then once you turn it on, then ANSYS kind of knows automatically to do this. But with that said, you can even still modify this further. Okay. And so if we take, as an example, let's say that we want to apply a 1,000 kilonewton load onto a beam. What ANSYS will do kind of underneath the hood, without you really asking it to, is that, let's say that we have 1,000 kilonewtons right here. Okay. And so what ANSYS will do is that it'll slowly ramp up your simulation up to that 1,000 kilonewtons, but it'll do this in several steps. Okay. And so it'll run, one simulation where the load is only, maybe a tenth of this. And then after that, it'll run another one automatically with, by increasing that by a small increment. Okay. And then eventually, you'll reach the point where you're at full load, but you approached it in several different steps instead of just going right up to the maximum load right away. Okay. And so it does this over a period of time. All right. Any questions on this? Okay. All right. And so, if you have a loading history like this, let's talk about, what you can generally expect from a linear simulation versus a nonlinear one. Okay. Actually, let me do this. And so let me go ahead and redraw the loading curve. Okay, and so let's say that we have our loading curve the same as the previous page, and so we ramp it up slowly. Okay. All right, and so the structural response, if your simulation was linear, just like we talked about at the beginning, the structural response should be directly proportional to the load. And so your structural response should also look like a line, right? Okay, and so if you ramp this up incrementally, it should look like that. Okay. But if you had a nonlinear structure, okay, for a nonlinear structure, you might get behavior that looks like this. Right? And so for the small deformations or for the small loads, you might have linear behavior. But once you get to the higher amounts of load, then the curve will start to deviate. Okay. Okay. And so in the end, you might get a higher amount of nonlinear deformation than before. Okay. All right, and so in general, what you'll see is that if you turn on large deformations, and if you ramp up the load slowly, then what you'll see is that nonlinear simulations will experience higher deformations than linear ones. Okay. Okay. Right. And so what that means for you as a user is that if you stick to just linear simulations, it's possible that you're underestimating the deformations. Okay. Right, because the nonlinear simulation is going to be in general more accurate than the nonlinear one. Okay. All right. And the number of element or the number of increments that you do, or the number of steps, this is something you can control as well. Okay. And so the more steps that you do, and so let's say that you apply the loads and under more steps than before, the more steps that you do, the more accurate your simulation is going to be. Okay. Okay. But of course, the more loading steps that you do, the higher cost the higher the cost is going to be. Okay. Okay. Because the more increments that you do, the smaller the amount of element distortion that you're going to get in between each step, which is ultimately a good thing. And so if you're curious about where you can set these steps, is you can do that within the setting called analysis settings. Okay. And so if you go into the ANSYS mechanical interface, you'll see in the project outline that there's going to be, I think it's under solution. No, I think it's under static structural. Under static structural, there's a button called analysis settings. And so we haven't done anything with that so far in the class, but all of these settings for how you apply the loads, whether you turn on large deformations, all of that is within that tab. Okay. And so next time you go to do a finite element simulation, I would say give this a try. Okay. And so large deformations or geometric nonlinearity, it's an issue, especially when you have large deformations. But people always say this is always the easiest one to fix, because all it really takes to fix it is to just flip a couple settings in analysis settings, and then you're good to go. Okay, so there's nothing really special that you have to do. You just have to make sure that certain settings are activated, and then you just be patient with your results. Okay, and so it's not that bad. All right. Any questions on this? Okay. All right. And so before we go to topology nonlinearity, I want to discuss a little bit about how nonlinear equations are solved. Because it's a little bit different than how a linear problem is solved. Okay. Maybe I should change this title: computational solutions to nonlinear problems. All right. And so, we've discussed kind of at the beginning of the class that, when when the computer goes to solve a finite element problem, essentially what it's doing is that it's forming a large linear system of equations. You can't actually do this in nonlinear problems because the equations themselves are nonlinear, and so you can't actually build a system of equations. And so you have to do some additional numerical techniques in order to work with the nonlinear equation. Okay? And so I'm not going to go into the details of those algorithms because they probably take a whole lecture and they would probably still make no sense. It hardly makes sense to me, honestly. But the name of the method, if you want to look into it, it's called the Newton-Raphson method. And it's a pretty, at this point, I'd say it's a pretty ubiquitous method. And so, I'm pretty confident in saying that, a lot of FEA softwares actually use this because it's just so effective at what it does. Okay. And so, again, we're not going to go into the details of that method, but but kind of one important detail about how it works is that it performs an additional approximation step. Okay. And what it's essentially doing is that it's taking your nonlinear equation and kind of intelligently turning it into a linear equation. Okay. Okay. But because of this approximation process, it's never going to be exactly the same as the nonlinear. And so there's always going to be a difference between the approximation or the approximate solution and the real, and the actual nonlinear, equation. Okay. Okay. And this difference is given a special name. It's called the residual. And the residual is an important quantity because you basically want the residual to be as small as possible. Okay. And so ANSYS is actually computing this residual and it's tracking it, with respect to some criterion. Okay. And so, as ANSYS is going about solving your nonlinear equation, what it's doing is that it's computing this residual and checking to see if it falls below something called the criterion. Okay. Okay. And you can actually check this. And so, as your nonlinear equation is being solved, and honestly, sometimes when you solve a nonlinear equation, you're going to have a lot of free time because it's going to take a while to solve. But you can check its progress. And so if you go to solution information, right? So this is another tab that's in your ANSYS mechanical workspace. Okay. And then you go to you have two options. And so you can either go to force convergence, or you can do displacement convergence. And after you click those, you'll be greeted with a graph. Okay, and that graph is kind of an indicator of how well your nonlinear simulation is performing. Okay. Right. So I know a lot of this section is kind of hand wavy, but the point is, I want to show you, what this force convergence is, what this displacement convergence is, just so that you can check and you can assess, how accurate or how well solved your nonlinear simulation is. Okay. All right. Any questions on this? Okay. And so if you check those convergence plots, it might look something like this. Okay. Right. So on the x-axis here we have time, and on the y-axis here we have convergence. Okay. What you'll see on that plot is that you'll probably see a horizontal line. You'll go through the plot. Okay. And so this horizontal line here is the criterion. Okay. And then in addition to that line, you'll probably see a curve, that may go up and down. So maybe it looks something like this. And this curve right here, this is your residual. Okay. What you want to see, or how you can check to see if your nonlinear simulation is well solved, is to check to see if the residual falls below the criterion. Okay. Right, and if that's the case, then your simulation is good, and we say that it's converged. The word convergence and the word converge is used a lot in finite elements, and unfortunately, it's used for different things. But for this case, what we say is that the nonlinear parts of your simulation are converged. And so I try not to use that word, just because we already have mesh convergence, which is another concept, and honestly, I think the more important concept. But when you do check these plots within ANSYS, that's the terminology that they use. So convergence is good, and so in general, you want your simulation to be converged across many different places, and then this is just another place where you can check convergence. Okay. All right, and so that's geometric nonlinearity, and so that's how you can account for large deformations, and also check to see how well you're simulating those large deformations. And so the next source of nonlinearity is topology nonlinearity. Okay, and this strictly has to do with how you define the connections between parts in an assembly. And so just like we say at the beginning, we say that nonlinear behavior can occur when different parts either slip past each other or otherwise separate. Okay. All right, and so, just to kind of give you an example, let's say that we have a 2-rod system. Okay, and so let's say that we have a rod like this. Okay, and this is supporting another rod like that. Okay. Okay. Let's say that we apply a force on this rod like here. Okay, where all of a sudden, this rod is going to slip. Okay. And so now, we have a situation that looks like this, where the rod has slipped. Okay, so maybe it looks down right here. Okay. And then the top rod is going to rotate itself as a result. Okay. Kind of a poor rotation, but it kind of the way I drew it kind of looks the same, but you can imagine it's kind of rotated down because it's slipped, right? Because this rod is kind of rotated like there. Okay. And so because we have this slippage, we have kind of a non-linear effect. Okay. And so, the way you can see that is, let's say that we take this force and we ramp it up slowly, right? And so we start with a very, very small amount of force. And so, when we start out, the force is so small that it can't overcome the friction between these two parts, right? But eventually, once this force can exceed that friction, then all of a sudden you have a very large amount of deformation, right? And so this part is going to slip, it's going to fall. This part is going to slip and it's going to fall. And all of a sudden we have a huge jump in behavior, okay? And so whenever you have kind of nonlinear behavior like this due to parts slipping or separating, that's topology nonlinearity. Okay, and a lot of what can happen, will be determined based on how you define the contacts between different parts. Okay. Okay. And so, one thing I want to cover today is, we're going to go through the list of all the different contact types that you can do, and which ones introduce nonlinearities, and what you can expect from the behavior of each one. Okay. All right. Any questions on this? Okay. All right. So let's go through all the lists of the different contacts that are available within ANSYS. All right. And so the first one is the main one we've been using for all of our jobs so far, and that's the bonded support. Okay. And so the bonded support are when are basically you're going to take your two parts, and wherever they're in contact, you're going to super glue them together. You're going to weld them together. They're going to be stuck together for life. Okay. And so when two surfaces are bonded together, what you're assuming is that their deformations are going to be exactly the same at that point, right? And so when one moves a little bit, the other one's going to move in exactly the same way because they're totally bonded. Okay. All right. And so with the bonded support, because there's no slippage and no separation that can occur, then there's no contact nonlinearities are introduced here. Okay. A lot of negatives now. right? And so that's a big reason why we've been using it. And so, with the bonded support, you don't have to worry about nonlinearities at all, because, there's absolutely no chance of it happening. All right, and so that's bonded. And so the next type of contact that we have is no separation. Okay. And so in no separation, the corresponding surfaces or edges or points are coupled together in the normal direction. Okay. Okay. And so the two surfaces are not allowed to separate. Okay. But the difference between the no separation and the bonded is that in no separation, it does allow a little bit of slippage, between the parts. Okay. But the magnitude of this slippage is assumed to be small. Okay. And so because of that, even though slippage can occur here, because it's assumed to be small, then this is the other contact type where nonlinearities are not introduced. Okay. Okay. And so it's very similar to the bonded one. And so it's not all that different. I would say that, the situations where you would want to use no separation versus bonded are situations when you don't want to transmit any or that many shearing forces in between surfaces. Okay. Okay. Because when you have two bonded surfaces together, and they try to slide past each other, there's going to be some significant shearing forces that occur in between the surfaces to make sure that they always stay together. But with no separation, when two surfaces try to slide, they're just going to slide with no resistance. And so, maybe you have one part that's having a force that's being, applied in shearing, but when you do non-separation, none of that shearing force is going to be transmitted to your other part. Okay. And so in situations like that, where you don't want that, shearing to occur, that's when you would pick no separation. Okay. But even just talking more physically, more plainly, you would pick no separation in cases where physically you don't have a bond support, and so you have two parts, and they're not welded together, they're not bolted together or anything like that, but you don't want them to separate from each other. Okay. And so these are the two options that you can choose when you don't want to introduce nonlinearities. Okay. And so you're basically safe to choose bonded support or a no separation support when there's you don't want to introduce nonlinear behavior. Okay. Questions?
Yeah, well, does this simulate like something that is rotating within something else. I mean, I think I talked to you about this before, where,
Mhm.
you know, with the midterm project, where you have the shaft and the housing.
Yep.
But you want those, all surfaces of both those components to be touching,
Mhm.
but you're not necessarily saying that they're bonded together. It's able to rotate within its axis.
If you were doing like a pseudo-static representation of that, so like for a static housing, you know, this
Right.
would be what you would choose. But if
Okay.
you actually want the thing to actually rotate and move a lot,
Well, then it would be a static analysis.
exactly, then you would use probably one of the other supports that we have.
Okay.
Because this assumes that there's some slippage, but it's small. But if you have like actual rotation, then that's a lot of relative movement. And so you'd use a frictionless support, which is what we're gonna go over next. Yeah, but this works great for a static situation. Yeah. Mhm. All right. Any other questions on this? Okay. All right. So let's go over the third support that we can do, and this is the part where we start to introduce nonlinearities. Okay. All right. And so the third support that we have is called rough. Okay. And so under a rough contact, the corresponding surfaces are free to separate. Okay. But when they are in contact with each other, then they're not allowed to slide past. Okay. And so basically what you're assuming with a rough surface is that the coefficient of friction is so high in between the surfaces, or maybe they're being pressed together, you know, with such great force that sliding in between them is impossible. Okay. And so you can kind of almost think of it as the opposite of the no separation, right? And so no separation says that they can't separate, but they can slide a little bit. But for a rough boundary or rough contact, they can separate, but they can't slide past each other. Okay.
What would be a good example of that?
I mean, I guess in reality, you know, any two surfaces in contact can always slide, but this is kind of an approximation where you want to disallow any sliding. And so, you know, if you have, you know, maybe two pieces of concrete, I would say, you know, and they're being pushed together really well, I would put a rough support on that. And so in reality, they could probably still slide, but because those surfaces are so rough, the friction force is so high, then you can assume that they're not going to slide past each other. Yeah. Mhm. Right. And so since this one does allow separation, then this is the first contact in which nonlinearities are introduced. Okay. Okay. And so if the two surfaces separate, then that's going to change the topology of your mesh. It's going to change the connectivity. And so that's going to be a nonlinear condition. Okay. All right, number 4. Number 4 is frictionless. Okay. Okay. And so under a frictionless, under a frictionless contact, there's no constraints at all in place. And so the surfaces are free to separate and they're free to slide. And more importantly, they're free to slide without any resistance. And so this is a no commitment, no committal type of relationship. Okay. And so since this places no restrictions, obviously this one is going to introduce non-linearities. Okay. All right, and then very quickly, just because we're just about out of time, the last type of contact that you can have is frictional. Okay. And so under a frictional support or under a frictional type of contact, separation and sliding are both allowed. Okay. But sliding only occurs when the shearing forces exceed the frictional force. Okay. Okay. And as an additional input, so if you choose to have a frictional support in your FEA, then you have to specify a coefficient of friction. Okay. And that's something that you have to research yourself, considering what types of materials that you're having and what's the coefficient of friction in between those materials. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. And so that's about halfway through the non-linearity lecture notes. And so, again, we'll pick this up in about 2 weeks. But next week, we're going to do another ANSYS activity. Honestly, I haven't made it yet, but I think it'll be one of the cooler ones because we're looking at optimization. And so optimization is one of the cooler features within ANSYS. All right, and so I'll stick around today to answer any questions you have on the project. I don't have any office hours for the rest of the week, but if you want to talk about the project before the due date on Friday, just shoot me an email, and I'm happy to set up any Zoom meetings with you. Okay, and so best of luck, everyone, finishing the project. Don't be afraid to reach out if you have any questions. And I'll see you guys in total next Monday. Okay, let me. I'll come to you. Let me organize it.
So it's across the street convergence, just to like justify.
Okay, sure.
And these are the graphs.
Literally or
Okay.
I'm wondering why I'm like.
It's honestly, it's really hard to get insurance, but with the limitations that you have for your reports, honestly, I think a lot of people are
half of the homework for you.
because I'll tell you the reality. The reality, even for a relatively simple geometry like this,
I'll be 20 minutes.
at the very least, like 500, 600.
I think so.
And so if you tell any professional engineer, they're going to think you're. No way. That's not to say that you can't do it. It is possible to get convergence, but you probably have to put it as a pretty light loading situation.
I got a little bit with deflection field and stuff.
Even then, you might say that this, but you at least want to see 3 or 4 different plots on the road to say that it's going to go.
So for a better chance to converge, what you said.
Yeah, and so generally, the lighter the load that you have, the less non-linear stuff is going to happen, and so it becomes easier to converge. So if you want, I mean, it's not a requirement for this problem. If you want to lower your loads, then you might get and then you limit the non-linear effects, and then even that, I think it might still be, especially for the stress.
Okay, so for the midterm, I don't really need to have. I don't like justify on which side.
You could just say that you minus fine is, so here's the, you can say here's the results of the mesh convergence that I did. And this says that I need to be as fine as I can. And this is the limitations of the software. And that's what I.
Okay, I have another question on the keywords.
Yeah.
I'm having trouble like knowing what exactly keywords.
Keywords are like the hashtags for your report. And so if someone wanted to Google your report, then those are the keywords that they use. So you can even think just like very broadly. So like finite elements, ANSYS. Which one are you doing? Are you doing
This is a hard top for a Jeep Wrangler.
Okay, so you're doing the are you doing the shaft house?
Yeah,
Okay.
Yeah.
So like shaft house, shaft, things like that.
Shaft. Oh,
Yeah.
okay.
I meant to put out an email for that. But this is a general template for this any scientific work. And so those keywords are for people who want to have their article. But for this class, everyone's kind of doing the same thing. So your keywords can just be like finite elements, ANSYS, things like that.
Okay.
Or you can leave it up. Honestly,
Okay. Cool.
that's what.
Last question.
Yeah.
So this is a setup. I'm trying to illustrate.
Okay.
I want to say it in the business because I kind of overthought it. The hard top weighs 150 pounds.
Okay.
But I'm applying the factors. Ignore the numbers. Say if it goes like 150 pounds down.
Yep.
And then this winch pulls the 150 pounds this way.
Sure.
Sure. Does that mean that there will be a resultant vector going down this way?
Yep, because you have a tensile force going down this way and also this way.
Okay, and that'll just be like a combination of this.
Yep.
Okay, thank you. So make sure.
Yeah, no, that's
All right, thank you for answering questions.
So I was doing the same thing. I was working at 200,000 elements and still not converting.
That's fine.
So
Yeah, it's if you don't get convergence, then it's fine. I mean, if this were a company and you had access to professional analysts, say you keep the point. But because we're limited, because of this convergence, just go as far as you can and say that and you can just say in your report that convergence is probably somewhere out there, and just do as far as.
So I have been like I'm keeping a course mesh, but where the concentrations are high, I would like to find it.
That's perfect. Yeah.
Because I'm doing like the optimization of the disk.
Mhm.
So on the disk itself, there are concentration, high stresses on the edges.
Mhm.
So I've refined that edge, and the center of the disk is all closed.
Perfect. Yep. Sounds good.
Okay, so 200,000 elements are fine, or
Yeah.
should I limit it to 50,000 or 60,000?
Go as far as the software are you using.
I'm doing it in the lab.
Okay. Yeah, just go as far as you can push it into the. Yeah.
I have like a one second.
Okay.
Are you?
No, it's not a requirement.
I'm hearing it, I'm like, okay.
Yeah, I'm surprised. No, it's one way that you can justify a mesh element size, but there's other ways that you can do it.
Yeah, I justified the integrity of the mesh through this.
That's fine. That's perfect.
Okay,
So it'll be a requirement on the final project, but the midterm project it's not a requirement.
okay, cool, thank you.
I think you raised your hand.
It's not a conventional version, so it's just to refine.
Okay. How did you get the professional?
Well, it's not work.
Oh, it should work. Okay.
Yeah.
Because people get it.
Oh, yeah, no. This is my work laptop. I do all 100%.
Okay. Okay. Perfect.
That's it, I guess. Okay, anyways. So I'm trying to figure out how to apply these lists. So pretty much I'm trying to like that this had like supplemental on it and a valve at the end of that. So it's just like a bumper that's clamped on right here. So the valve is clamped on.
Yep.
Would this be the proper way to apply force?
we have a clamp that's being put around.
Yeah.
Yeah. So so right now you're applying the load in this. The clamp is gonna surround it in quite a normal way.
Okay.
And so instead of components, you can change that to normal. You might change it to pressure. Because the pressure load gives you the option to apply it to. And for circular surface like this, it ensures that the force is going to be perfect. I think that's more realistic for a plant. Just applying, because right now just applying.
Okay.
So that would be something that's any company.
Yeah.
Which you can do too. If you want to do a plant, then I would do it.
Okay. Sounds good. Because yeah, that's kind of what's happening. Fixing your climate. Yeah. Okay. So is it enough changing boundary conditions to kind of keep it where it's fixed, right? But on top of the clamp load, I add like pressure inside, and I was gonna add a hydrostatic pressure, but that was what I was gonna ask. I'm trying to apply both these well, and I'm not exactly sure if I'm doing it.
Yeah. So the pressure one, okay, it's on. And so the pressure load is going to apply kind of a uniform pressure to every surface. Hydrostatic pressure is actually a special type of pressure. And so if you click it, yeah, as you can see that the pressure varies, right?
Yeah.
And so there's a red portion of the fluid. And so thing with hydrostatic pressure, if you have a fluid that's still, then the pressure is going to vary. Okay. So the deeper you go, the higher the pressure is.
Yeah.
And so this is kind of it's almost like a shortcut type of feature of it, which can do. So based on the height, and based on where you define P0, okay, then it's going to increase the pressure as you go.
Oh, okay. So it's not like fluid.
No. Yeah, so it's
So
I would say I would just say because normally you only apply hydrostatic pressure when you have two things. Okay. And so if you're saying you're going to find out
Okay, no, of course I need that is.
then you would apply that. Okay. It would be kind of a simple way. For this, you can just do a constant pressure.
Okay, so I can just do this one.
Yes.
But even though this air is going this way.
It's not, I can see it's not.
Okay. And then the last question, the idea is that's this.
I would at the very least suppress the alternative. Or is that part of your question?
Yeah, it's. Yeah.
But normally they're small. They don't really have. Normally don't really have anything specific.
This all of these.
Yeah. If you're not considering the plunger or that gasket at all, it's just going to be. If you look at your simulation, or you have your oh wait. Yeah, so you see that entire thing is all.
Yeah, exactly.
Yeah, so if it's all blue, then it's not contributing.
So just adding the pressure.
So
do I need to change? Do I need to change fixed support?
So when I say two different boundaries, what I mean is two different loading scenarios. Okay, and so right now you have one scenario where it's really turn on pressure.
Yeah.
And so that's one.
Yeah, and I was just gonna do the one that was just.
Oh, just okay. Yeah.
Yes.
That's fine. So those are your two conditions. And then your third situation.
Yeah. Okay.
Yeah,
Thank you.
perfect.
Appreciate it.
Yes, I would be careful using the professional one because it's easy to get power or refinement. But if the simulations take longer than 10 minutes to run, just kill it.
Yeah, I talked about that.
Okay, perfect. Yeah, no, I don't want you waiting on hours.
No, thank you.
Yep. Let me go answer your questions. Yeah, so for the discussion conclusion, so that's going to be after your finite element, right? And so your finite element results, you're going to get things like deformations, things like stress. And so your discussion will be the places where you discuss, based on the deformation, based on the stress, then, this part is gonna fit with this number. Or you discuss, maybe we can make the goal from a Google design. So it's, think of your final results of that data from the experiment. And your discussion is, what can you say?
So that's what you actually raw, so I have to.
Yes. Yeah, so your final element result should be just your figures, and it should be just a brief description of here is my deformation plot, here's the master deformation of this, here's where it goes. And then your discussion is where you actually. Conclusion is kind of a summary of the whole. Yeah, and so it's I think of it as almost like kind of like your introduction, but kind of flipped upside down. And so your conclusion kind of starts with kind of the specifics of your whole report and then kind of broadens it out. It does, yes. I do have a quick workshop on it too. And so unfortunately, I don't think we're gonna get to, well, it depends, I have so many like extra topics that I can discuss against this. And usually what I do is I just have them like 20. And so I have all these like small workshops I can do, and I usually just let the class go to which one. So I have a heat transfer, I have fatigue analysis, I have a workshop on how to do anisotropic material. Yeah, positive materials. Yeah, I have a bunch of them. So I think for the mass, maybe week and a half of the class, I'll let everyone go on what they want. So I have fluid mechanics, if you're and so I'll run a poll and see what people want to see. But anyway, I have everything typed up as a PDF in terms of instructions. And so I'll send those to everyone so you can have access to it. But I'll only be able to cover a subset.
Just so you know, for this part,
yeah,
the max you can choose for this.
For the friction. Oh, okay. Okay.
If you pick over 0.2, it would say that it's license.
Oh, interesting. Okay. Oh, I had no idea there was a description. That's good. Okay.
Perfect.
Yep.
Yeah, we have
Change the material.
so is it okay if I like so if I reduce the thickness of the disc instead of doing that
Yeah, that's fine. Yep.
my one condition is that the wall is open, I will find pressure inside of the wall.
Okay.
Like that. Second wall, and then apply pressure right inside.
Yeah. Sounds good.
Then if there is a need, like where the high pressure is like when the wall is open or when the wall is closed, I will then change the thickness and then reapply the same one.
Perfect. Sounds good. Cool. Yeah. Are you any questions? Okay. Yeah, if you have any questions, I'm probably gonna head out right now because it's after 7. But if you have questions, just yeah.
Thank you.
Yeah. Raphael, did you have any questions before I head out? Okay, all right, I'm gonna close up shop. Okay, all right, see you.